These are the notes on the ideal gas law. Please download the notes from Schoology so you can follow along. We've been talking about gas laws previously, but haven't been discussing a few things as we've been looking at how pressure, temperature, and volume are changing. Today, we're going to look at what happens if we add more moles to a system and the relationship between pressure, volume, and temperature as we start to consider moles. With this, if you want to start, pause the video and draw a little model and think about this question. Thinking of if we draw a balloon filled with 10 moles of gas and drawing dots to represent a mole. Feel free to pause as you do this. I'm going to just go ahead and draw mine. As I'm drawing this, I just kind of drew my balloon of a medium size. 10 moles means I'm going to put 10 dots in here. 1, 2. Now that we've done that, take a minute and predict how the balloon would change if you added 5 more moles of gas. Think about what would need to change and sketch that out where it says predict. As you can see, I added a few more dots to my balloon. My dark blue dots represent my original 10, and now I have, with those light blue dots, 5 more, meaning that 15 moles of gas total are in my balloon, showing that I have 15 dots. Think about what would have to change. When I drew my picture, maybe you drew yours differently. I drew mine showing that it was the same size. So as I'm looking at this, I'm considering that if the volume stays the same, then what's going to happen is that if my temperature also stays the same, maybe I'm going to need, maybe the pressure inside my balloon is going to increase, because if the volume is the same and let's say the temperature is the same, meaning the length of my arrows, what's going to happen to the pressure? I'm going to have more collisions if I think about what's going on inside my balloon. If instead of having the volume the same, the temperature the same, and the pressure the same, if maybe I kept the pressure the same and changed the volume, pressure stays same. Well, what would happen to my volume if I want those collisions to stay the same? My balloon might have to get bigger. So we have some different things that we need to consider as we're now changing or adding more moles of gas into our pictures. I didn't draw the arrows on these, but you could have drawn those arrows. For the sake of time, I'm going to just leave my models at that. Now, what we're looking at including is we're going to be including the number of moles of gas, or how much gas we actually have, as we look at our next gas law. So the ideal gas law is the second kind of big law that we have along with our combined gas law. And the ideal gas law states or relates pressure, volume, and temperature for a given mass of an ideal gas. And this says mass in here. We're going to really use moles to represent that, to say how much gas do we have. And we can see that equation off to the right. You might be wondering, what is an ideal gas? So the ideal gas law, this is an ideal gas is a hypothetical gas where the molecules don't attract or repel each other. So when we're using this gas law, we're assuming that the gases we're working with are ideal gases and that they don't have charges, something we haven't had to talk about much, or we haven't talked about. And so this gas law just has us assume that we're not dealing with that. And so when we're using this ideal gas law, the equation we're going to have, and this would be helpful to add to your periodic table, is that PV equals nRT. P is pressure. Again, our standard unit for pressure is going to be ATMs. We are still using that variable P. Volume, still using our variable V. Our standard unit is going to be liters. N, we haven't been using as a variable yet. N stands for the number of moles, and our unit for that is going to be in moles. R is brand new. We'll talk about that in a second. And then T, that capital T for temperature, our standard unit is Kelvin, and we've known that we need to convert any temperatures to Kelvin if we are using those, because Kelvin is our standard unit. This R value is a new value that we have not seen yet, and that R value is a gas constant, meaning that it's going to be a constant number in any of our problems, and R is equal to 0.0821 ATMs times liters, atmospheres times liters, per mole times Kelvin. And you can see down here in this unit for R that all of our standard units of pressure, ATMs, volume, liters, moles, and then Kelvin for our temperature, all of our standard units are there, which is why having standard units is important, so that they match up with our values in our constant R. I would encourage you to add this value for R to your periodic table, along with adding the ideal gas law to your periodic table, so you have that as a reference. Now let's look at how we would use this. In the past, we have been looking at problems where we have maybe two temperatures and we're looking at a change in temperature, two pressures, we're looking at a change in pressure. We're going to recognize these problems because our problems are going to ask us for how many moles of nitrogen. That's one way we can recognize that this is an ideal gas law problem and not a combined gas law problem. So first way we can recognize is that we are dealing with moles in some way. The second way we can recognize this isn't an ideal gas law problem is because we're only given one value for our pressure, temperature, volume, and our N moles. We're not given that change with that. All right, so I have this first one kind of set up for us as I look at example 1 with my variables that we're now going to have kind of off on the left, so I can list those as I read my problem. If I have an unknown quantity of nitrogen at a pressure of 15 atm, a volume of 31 liters, and a temperature of 87.5 degrees Celsius, how many moles of nitrogen do I have? And how many grams of nitrogen gas do I have? So this is going to be a two-step problem. First, we're going to find moles using the ideal gas law, and then we're going to do a moles to gram conversion. So going through my problem again and looking at what I'm given, I have an unknown quantity. Quantity is going to be how many moles do we have? That's our N value, our new variable in this ideal gas law. So that's what my unknown, that's what I'm looking for. At a pressure of 15 atm, a volume of 31 liters, and a temperature of 87.5 degrees Celsius. I know I'm going to want that temperature in degrees Kelvin, so I'm going to add 273 using that conversion just like we have in the past. So that's going to give me 360.5 Kelvin. And now I can take this information and plug that into my ideal gas law from the previous page. So we have PV equals nRT, and all of these are multiplied by each other. Pressure times volume equals moles times R times T. So solving is going to be similar to what we've done in the past. So I have pressure 15 times 31 equals N is what I'm looking for. I listed our R value for us over here. R is always going to be the same in every problem. We just have to remember we have it. Times T, 360.5. And just like in the past, you can use whatever algebra you're comfortable with to solve this. I like to go through and multiply my values together. So I got 15 times 31, 465 equals N times, and I'm going to multiply my 0.0821 times 360.5 to get N times 29.597. I want to get N, number of moles by itself. I can do that by dividing both sides by my 29.597. And when I do my that 465 divided by 29.597, I can find that value of N. So N equals 15.71 moles of nitrogen gas. N2, that was given to us up here. Nitrogen is diatomic, and that's going to come into play in that second part, or the second question that's asked. And I just rounded to 2 decimal places like we have in the past. All right, now looking at my second question, how many grams of nitrogen gas do I have? So in that first part, I found how many moles I had. Now in my second step, I'm going to go from moles of nitrogen to grams of nitrogen using my stoichiometry chart from a few units ago. So I've got that value, 15.71 moles of nitrogen, and I'm staying within that substance. So this is just a one-step conversion. 1 mole of nitrogen, and you can reference your stoichiometry chart if that helps, is going to be the molar mass of nitrogen. So I go to my periodic table. Each nitrogen has a mass of 14. And because this is diatomic N2, that means we're going to have 28 grams of nitrogen. And in order to do that calculation, I'm going to multiply my 15.71 times 28 to get 439.88 grams of nitrogen. So that second part was just a conversion like we've done in previous units. All right, not every problem is going to ask us to find grams. Let's do another one. If I have 7.7 moles of gas at a temperature of 56 degrees Celsius and a pressure of 9 atm, what is the volume of the container that the gas is in? So because we're asked for moles, that's one indicator that this is going to be an ideal gas law problem. Also, because we were only given one temperature, one pressure, and asked for volume, that's another indicator that this is an ideal gas law problem. So looking at my variables, P, V, N, R, T, I just like to go through and list those in the same order that my equation is. Pressure, 9 atms. I can see that with the unit. It also tells me right before that. Volume is unknown. What is the volume? So that's our question mark. N is moles, so 7.7 moles. R is a constant, so we always know that R is 0.0821. And then my temperature, 56 degrees Celsius. I know I'm going to want that in Kelvin though, so I'm going to add 273 and I get 329 Kelvin. And just like we were doing in class, if you're worried about accidentally using that 56, keep your work there, but cross it off just so that you visually have a reminder that that's not the value you're going to use. All right, plugging these into our formula, that ideal gas law, PV equals nRT. I have 9 times V equals N is 7.7, R is 0.0821, temperature 329. And again, we're solving for V, so I'm going to multiply any of the numbers together that I have. 9V, that left side, we don't have anything to multiply, and then I can multiply these 3 numbers together. I got 207.98393, and I just kept a bunch of digits because I'll round at the end. And then to get volume by itself, I'm going to divide both sides by 9, so divide that 207 number by 9. So volume equals, and I got 23.109. So if I'm rounding to the nearest tenth, that would be a volume of 23.11. And then we need to make sure and include our unit for volume, which is liters. All right, last problem. Feel free to pause this and go through this problem if you want to try it on your own. It's another two-step problem. I have an unknown quantity of bromine. So unknown quantity, that means we're asking for how much. That's our moles N. In a 52-liter container, that's our volume. The gas is at a pressure of 8 atms pressure and a temperature of 380.5 Kelvin temperature. How many moles of bromine gas do I have and how many particles? So first we're going to find moles, which is N. So P, V, N, R, T, those are my variables. And I'm going to just list those out so I have them organized. Question mark because moles is my unknown. R, we always know our R value. So make sure you have that written and put a little star so you don't forget that that is a number we know. And then my temperature. Already in Kelvin, so I don't have to convert that temperature, which is nice. And then I can plug those into my ideal gas law, which is PV equals nRT. My pressure is 8, volume 52, N is my unknown, R 0.0821, and our temperature 380.5. All right, and I just paused that and solved that through. Feel free to pause the video if you want to solve and check that you got the same answer as I did. So for that part one, finding our moles of bromine, I got N equaling 13.32 moles. Now that second part, looking for how many particles. So to find the number of particles, I'm going to take my moles of bromine to particles of bromine. And again, you can reference your stoichiometry chart. I have 13.32 moles. And to go from moles, so 1 mole on the bottom, to get that to cancel, I'm going to need, that's going to be 6.022 times 10 to the 23rd particles on the top. And to solve, again, we're going to multiply our 13.32 times that 6.022 times 10 to the 23rd. And in doing that, I get 8.02 times 10 to the 24th particles of bromine, Br2. Bromine is diatomic, but that, because we're converting with particles, that does not affect our conversion factor. After this, you should be prepared to do the ideal gas law check-in and work on the ideal gas law worksheet. Let me know if you have any questions, and feel free to go back and rewatch any of this as you need.